What you're looking at is a Furman AR-1215 commuting tap voltage regulator doing something called hunting. As you see, it thinks the input voltage is varying between 120 and 115 volts, when in fact, the input voltage is pretty steady. There's nothing changing there. And so what's happening is there's a error somewhere in the control logic of this particular device. It's done this since I've bought it. And what I'm going to do here, I'll turn on the bottom one, and as you can see, I've got two Furmans in this rack. The bottom one and the top one are both connected to exactly the same circuit in my house. Notice the bottom one is saying there's 120 volts flat. There's nothing happening yet. The top one is insisting that the voltage is fluctuating, and it's having to modify its input settings to keep the voltage output steady. This is just plain not true. Now, this thing has done this since I got it. And I got this thing a long time ago, probably about 15 years ago. It's been sitting in a storage unit in Juneau, Alaska for the last 10 years. But it was doing this when I put it in the storage unit in Juneau, Alaska. So I know we've got something to fix here. So what we're going to try today is to fix this thing. I got an idea about how to fix it. I hope I'm right. We'll see what happens. All right, now I've looked online for the schematic for a Furman AR-1215 voltage regulator, and I cannot find one anywhere. I suspect, this thing is still for sale or some model of it. The circuit is proprietary. They don't want people to get their hands on it. So I'm going to have to guess how this thing works based on the generic model of a commuting tap voltage regulator. So that's what I'm going to do. I'm going to take a good guess here. I do not know exactly what's inside that little box. So this is an attempt to figure out exactly what we're looking at. So let's try to get the concept here. We've got an input voltage coming in here from the left, and that input voltage can be between 100 and 140 volts. Why? Well, you may be outside plugged into a generator. Generator may be running out of gas, the voltage is too low, its regulator's out of regulation, it goes way too high. So what you've got is the possibility that the voltage is not going to be at 120 volts. Now, I'm talking about US here. I'm not talking about Europe. I know in the UK you got a 220 coming out of the wall socket. I know in Japan you got 100. This is US, and US we're about 110, 115 to 120. So we got okay, so the supply comes in from the left. The two wires come in, and they wrap around this donut. This donut represents the core of a toroidal transformer. They wrap around some number of times I'm going to call N1. And then there are outputs that wrap around some number of times I'm going to call NX, where X can be 1, 2, or 3. And the ratio, the voltage out is the ratio of the voltage in over, the number of turns for the input over the number of turns of the output. And that's, transformer theory. You guys can go look that up. You don't need me to show you how these toroids work. All right, now, so you're going to have a certain voltage coming in, and you're going to have certain voltage coming out depending on the ratio of the turns of these different things. Now, what you're going to see here is that these output voltages are all going to be some ratio of the turns into the turns out, and one of them is going to be the correct voltage. One of those voltages is going to be between 110 and 120 volts AC for US. And which one? Who knows? It depends on what the input voltage is. But one of them is going to be correct, depending on, as long as you don't go over 140 or under 100, one of those is going to be within the right spec. So how do you figure out which one to turn on? Well, there's this control logic. That 5-volt control logic senses the input voltage and then figures out which one is at the right output voltage, and it's going to turn on a switch. One of those switches here is going to turn on a switch, and that switch is going to direct the output of that particular circuit to the output, and you're going to be sure that it's 120 volts for US. Again, this whole thing could be different for the UK or somewhere else. But that control logic is sensing the input voltage, and it's sensing the output voltage, and it's a control loop. Now, all you engineers who are studying control theory, get out your books and go figure it out. If you're like me and you've forgotten your control theory, like most of the people in the world, you're not going to know what the heck to do. But somewhere in that loop, things are getting messed up, and it's creating an oscillation. Now let's take another look here at what, how does this control logic switch? Okay, so each of those switches is going to pick which one comes to the output. Now you see, that's a 0 point. And AC voltage starts at 0, it rises, it falls, 60 times per second in the US. We're at 60 hertz here. And each one of these different circuits is creating a different voltage peak level. You're starting at 0, you're rising, going up and down, and it's like 120 times per second. V1, V2, and V3 each have a different peak. Now, one of those is the correct one, and it's being chosen by the control logic. When you switch, and you want to pick that one, for instance, when you switch between one to the other, you want to switch at the 0 point. You want to switch when the voltage is the lowest, right there. Now, why do we want to switch at the low point? Well, because let's say you have something plugged in and you're drawing some current. If you switch at the high point, the current is going to be at a max. Now, the current is oscillating along with the input voltage, up, down, up, down, up, down. And so what you want to do is, if it's a pure, I guess for all you electrical engineers out there, we're presuming a purely resistive load, which is probably not practical given what we may have plugged in. But okay, let's presume a purely resistive load. That means the current is switching in time with the voltage. And so we want to switch when the voltage, or actually the current, is at its absolute lowest point and not moving input or out. Because if you switch when the current is flowing, you're going to get a spark somewhere and you're going to blow something up. You're going to blow up your sensitive amp or your sensitive synthesizer. You've plugged something in here that you want to protect, not that you want to destroy. So you want to switch at the 0 point. So the control logic now is doing a bunch of things. One is it's sensing the input. It's figuring out which output coil we should connect to, which are the many secondaries, so that we get the right 120 volts. And we want to also make sure that we don't switch until we get to a 0 point. So it's doing all of those different things. All right, now let's see what we got inside this thing. All right, here we are on my computer desk, because I don't have a workshop. I got a workshop, but it's all full of junk. We've got to work on the sensitive electronics here, where the coffee is that can be spilled. Let's have a sip. Let's see if we can make heads or tails out of this thing. So the first thing you see right away looking at it is the giant toroidal transformer that I told you would be in here. Which is really no surprise. I knew it was in here because I had opened this up before. But these things generally have toroids. They're much more efficient. They're less noisy. That's why they use them in audio applications. So here, down here, way down here is where the power is coming in. So this is the input power cord. Input power is fuse protected by this fuse here, and protected by this, I presume, MOV. So the MOV, what that's going to do is it's basically looking for spikes. So if you get some kind of transient spike, it'll flatten out that spike for you right away. These things are sacrificial components. If it sees too many spikes, eventually it's going to fail. So these things either fail open or closed. If it sees too many spikes, it's going to fail open, we hope. In which case, it's like nothing is there. And that's okay. Then you just don't have that level of surge protection. If it fails closed, then your input current is shorted, and probably the fuse will blow and other bad things will happen. But in any case, these got to be replaced eventually. Now, I don't know if this one's good or bad. This unit, as I said, is at least 20 years old. The board has got some indications on it that suggest it was built in 1998, April of 1998. Thing is almost old enough to drink. So in California, that is. So this here is a filter. So what this is going to do is any kind of regular sort of pulsing, or this circuitry here might make some noise, and this prevents the noise from getting back into the line. The switching noise, anyway, when this thing switches from tap to tap, it actually makes a funking electrical sound, and you want to prevent that from getting back into the line and screwing up some of your other components. Similarly, some of your other components could be doing the same thing. So this is a filter, AC filter. This says 1998 on it too. I don't know if you can see that, but that's what it says, 1998. Yeah, we're pretty focused, so you might be able to see that. These are the input switches. So as I said, the input voltage comes here into this toroid, and then And let me just hold this up so you can see there's the outputs. And the outputs themselves are each protected by these little blue things, which are more MOVs. They're preventing spikes from getting out on the outside. Or if any of these cause a spike, if any of the devices that you've plugged in is spiky, it'll prevent those spikes from getting into that circuitry, which is more likely what would happen. Alright, so if we move over to this side here, so what we see is, here's the main transformer. This little transformer over here is just peeling some power, some of the mains power off, and it's turning it into 5 volts to run this circuitry. This circuitry here all runs off of 5 volts, and this gives you the 5 volts for that. And there's a voltage regulator right here that creates the 5 volts for you, and you're fine. As you can see, there's lots of wires coming off of here, and these wires create different voltages per input voltage. So you get a certain input voltage, and the highest voltage, I believe, is up here, and the lowest voltage is down here, and you get 1, 2, 3, 4, 5, 6, 7, 8 different voltages. And what this circuitry is doing on this side, these are all the switches. There you can see. Look at that. So these are each triac switches that switch the power in or out, depending on whether this control circuitry tells it to go on or off, and applies that power to the mains. This real thick bus here is the mains output. And then there's some LEDs that show you where you're at, and we'll take this board out and take a look at the board, but I just wanted to show you how it looked compared to our diagram. So again, voltage comes in, we get, for any input voltage, we get a number of voltages, 8 different voltages, higher or lower, can be higher than will be higher than the input voltage, some will be lower, and then this circuitry selects which one is closest to 120 volts AC, and using these switches, that particular line to come into this output, which goes out these down here. Okay, just for the fun of it, I thought we'd try to read what the voltages were at each one of these taps, just to see. So the actual output voltage right now is being regulated to 122 volts. That's the main output voltage. Alright, so let's see if I can do this without blowing anything up. Alright, so this highest tap here, there's a red one down here. We're getting 103 volts off the red one. Off this orange one, got 108. Off this one, this yellow one, we got 113. Green one is giving us, if I can get the probe onto the green one, 116 on the green. The blue is giving us 123. 128 on the purple. 134 on the gray. And the brown is at 140. So probably the one that's being selected as the output is, oh, it's not that one. One of these is at 123, this one. So this blue one is the line that is being selected as the output right now, and it's not oscillating. And in fact, it is the 1, 2, 3, 4, fourth one, fifth one. This is the low side. 1, 2, 3, 4, the fifth one. And if we look, I don't know if you can see, but the fifth LED, which is this one, and we're looking at it from the back, but 1, 2, 3, the fifth one is actually on that one right there. So that's telling us that the voltage is coming in, and the line that's being selected is this one. You saw all the different voltages here. This is the one that's being selected. You got 140 volts here, and 103, do we say? 103 down here. So for this given input voltage, you have that selection. Now, this input voltage could rise or fall, or rise and fall, and these voltages will all rise and fall, but one of them is going to be the right one as long as you stay within the 100 volt to 140 volt range. All right. Now we could debate whether or not the right thing to do is for me to, show you how I get this whole board out and everything. I mean, this is just mechanical stuff. One of the things I wanted to talk about, though, is whether you even need a device like this at all. When I bought all my sound equipment back in the 90s, the idea of not protecting your high-end equipment was just, that was heresy. So you use surge protectors, you put MOVs everywhere, and you use a device like this if you wanted some high-end protection. Well, the truth is, what are you plugging things into now in the year 2015? Well, you're plugging things into the wall socket, which is pretty highly regulated. I mean, unless, you got an overhead line that gets hit by a lightning bolt, chances are, even if well, this is not going to protect you against lightning. Let's get that perfectly clear. This will not protect you against lightning. Nothing will. You need a a lightning arrestor for that. But little spikes online, people turning motors on and things like that, you're just not going to have the kind of problems you think you're going to have. And most of the people who sell these things are making money off of your paranoia. This particular device was made for long-term major sags or increases in power. This is meaning, over the course of minutes, you get a drop of down to 100, or and you'd have to figure out which one of these switches was the right one, etc. You're just not going to have that situation these days, and with modern equipment. There's a debate on the internet, and you can read a lot of the blogs. So what you're going to find is that people just don't believe you need these things anymore. If you're in a professional situation, you've got generators that are well regulated. You got house power that's well regulated. You're just plain not going to need something like this, especially for a home user like me. You're just not going to need something like this. So, good thing I don't really need this. I got one that works, and I don't really need one. These MOVs, they die. There's modern techniques that you can use that are a lot better than this. But let's fix this one because got nothing to do, and it's a Saturday.
All right, let's get in here and look at this board and see if we can figure out if there's any way we can debug what's going on here. What do we know? We know that there's a zero crossing switcher, and we know that there's a comparator in here somewhere, and we know that there are these switches. So at the very end of the day, these guys are switching between the different voltages, and honestly, it doesn't seem like there's a problem with that. It seems like these things are switching just fine. I'm not sure there's a problem with any of these switches. If there was an issue with the zero crossing, I shouldn't do that. If there was an issue with the zero crossing, we'd have bigger problems on the output. So I don't think it's that. I think it's the feedback loop between whatever is sensing the input voltage and judging what that input voltage is, and then turning one of these switches, sensing the output, and seeing if the output's in the right range. That loop is somehow defective, and if I were a betting man, I'd say it has to do with whatever's comparing the input voltage. The input voltage comparator is wonky somehow. Now, what is a comparator? Let's see what chips we got here. Okay, now I've looked up what these things are, so it's not that I'm a genius and remember this. I actually looked them all up. So this here is logic. This is an HC7404. This is a bunch of inverters, a very, very simple circuit. There's not much to it. Could that be wrong? And seeing as how I don't have the schematic, I don't know exactly what inverter is doing what. Now, the inverters are probably working. Have they shifted in voltage somehow that perhaps maybe they're switching at a different point? Maybe. The thing is 20 years old. It's possible that's happening. I happen to have another LS7400 series chip here. And why do I just happen to have one? Well, because I live in Silicon Valley and these things are ubiquitous in old equipment. This is new old stuff, but this is an SN 7404, and that's a CD. This is ancient. This is a CD 7404. This is an SN, and I got to look at the data sheets to see if I can just wantonly swap out SNs for CDs. Not sure. This is here the voltage reference, and you can see maybe you can't see it, but there's a little indication here that you should get 2.5 volts. This reference should give you 2.5 volts no matter what. So what's coming into this is the 5 volt AC that gets rectified by these bad boys over here. There's little filter caps, and so you get 5 volts DC running all this logic. That 5 volts is seen by this voltage reference, and you get 2.5 volts here. And even if this floats a little bit, which it might do if the input voltage is floating, this should still be 2.5 volts. Now, you got this voltage regulator here, and unless this is bad, I can't imagine this floating. But if this guy floats, oh, you got a bad problem. Then you're totally out of whack. So in fact, I'm going to replace that just for the hell of it, because I happen to have a whole bunch of new ones of those too. So I'm going to replace that too. This guy over here is a TL-084 CN. So this is a set of quad op amps. Now this is the comparator. I'm guessing this does two things. I'm guessing some of these op amps actually are doing the comparison of the input voltage to the reference, and some of them are probably being used in the zero detection. If this guy is bad, you definitely have problems. This is a CD740-138. This guy is a set of D flip-flops that tell you what state you're in. I don't know. That could be bad, but could be. I don't have a replacement for that, so it better not be bad. This down here is an SN. Well, I just happen to know this is a multiplexer. And the fact that all the lights change and these change in sequence says to me the multiplexer seems to be working fine. And this is secret sauce. This is a PAL, a programmable logic array. There's no way for us to know what this is doing. They programmed this back at the factory in 1996. It does something, I don't know what. If I had a lot of time and nothing to do, I could sit around with a logic analyzer and shoot inputs to it and see what comes out and come out with a truth table. I'm getting too old for that. I'd rather be doing other things with my life than figuring that out. So I'm going to hope that this is not bad. Again, I think the problem is in the feedback loop. Now, what that also means is that some of these high-end resistors, especially these blue ones that are very high precision resistors, one of these could be fried, or it could have a bad connection. Not sure what. We can be pretty sure that this stuff over here is for rectifying and generating the 5 volts to run the circuit. We can be pretty well sure that these are the switches. We can pretty well be sure that this has to do with the switching. This guy's probably got some secret sauce to figure out when to switch and when not to switch. This down here is your over voltage protection. So this is gonna, if you go over volt or under volt, this guy is gonna turn you on or off completely and shut the circuit down. Now, other things. What are these little white things? These are optical isolators. So these are on one side. Inside here is an LED and a optical receiver. So when you apply voltage on one side, the LED turns on, the optical receiver turns on, and the switch goes. So what this does is isolate the 5 volt logic from the 120 volt output. And that's how you can switch these 120 volt things with these 5 volt things. So that's basically what's happening. Now, what I'm going to do is I'm going to look for the feedback loop. I'm going to replace this guy is definitely in the feedback loop. If he is heat sensitive, and you know, I've measured that output voltage and it sure doesn't look like it's moving around very much. I'm going to change that anyway because I have one. If this old TL-084 is wonky, that could cause some of the problem for sure. If any of these resistors goes out of spec when it gets too hot, that could be a problem. If one of these switches for some reason doesn't switch right and it's sensing the switched voltage wrong, that could be a problem. So I might replace those because I happen to have some. And these are high-end, very precision electrolytics. I'll test those. Although I got to be honest, these guys don't look like there's anything wrong with them whatsoever. And then there's a fuse here to protect this logic circuitry. And I'll test all this. I'll test all of these caps and make sure that they're in spec. Okay.
All right, I got to come clean here now because I've actually done a couple things with this board already. One reason it's not hunting like it used to is that I have already replaced a couple of these things. So, for instance, this TL-084 is one I put in. Now, it's new old stock. It's really old. I don't know where it came from. I had it in my junk box. It replaced a TL-074, so this is a higher end component in terms of noise. But you know, the thing is, I just don't know how old it is. And let's see if you can see. I've actually got some brand new TL-084s. I'm going to replace that. I'm going to replace this guy because I can. Nowadays, those things come in these SO4, SO8 packages, so they're made for surface mount. I've got some of these little surface mount board things that I got online. I'm going to put this on the surface mount board, and I'm going to turn it into a through hole with some pins, and I'm going to replace that. So I'm going to replace this again with a even newer one that I've got. I'm going to replace that. I might replace this, but you know, the chances that this is bad are small. I've tested all of these resistors, all right, to the best of my ability. Well, those are not resistors, those are diodes. I've tested these resistors to the best of my ability. You know, testing a resistor in circuit is no guarantee you're going to get the value that it states because it's connected to other things, right? And I don't have the schematic, so I can't figure out what it's in series or parallel with. And you know, but they're all seeming good. These caps don't seem so bad. I'm guessing that this weird-looking cap way down at the end here is one that controls the dampening for the feedback loop. This looks like some kind of not polycarbonate, but poly cap. Low leakage. I've got a couple of these laying around. I might just replace that for the hell of it. If I slow down the feedback loop, which is really what I want, I might stop the hunting. Like I said, I can't do anything about this PAL down here in the bottom. That's their secret sauce. I don't know what to do about that. And I may replace, just because I have them, some of these triacs, and especially the ones that are on the blue and the purple, just, you know, in case they are, you know, there's something with those. Now these switches, I've actually got some of these. Chances of these being bad are pretty low. Maybe one of these caps is bad. One of these, it's a 104, so it's what, a 0.01 microfarad, 10 nanofarad cap. Maybe one of these resistors, you know, because this is controlling the switching mode. Could be, you know, or let's say reducing the possibility of any spikes when it switches. It could be, maybe not. You know, some of these parts are perfectly fine. Now, if we look at the board, one of the things that you'll notice is up here on the top, this looks kind of wonky, and the reason is because I replaced this resistor. This resistor had a connection that looked pretty bad. It was one of these, you know, 5% resistors, carbon, and I replaced it with a higher end precision resistor some time ago, and you know, this is just that's flux, and I've actually tried removing the flux. You know, could this be causing some trouble? Could be. I don't know what this diode is. Chances are, but it tests good, so I'm not going to replace it. Here's another high-end resistor. It looks good. This is a little cap. Could this be part of the problem? Possibly. This is not a resistor, it's a capacitor, and you know, I might replace that with just because. So I'm going to go forward and replace a lot of parts because I don't have a schematic, and there's no way I can test this to know that it's functioning correctly, except to know that it's switching too much. Right? So what I'm going to do is just start replacing things. Yeah, it's Saturday. Let's replace. So these are just these little boards I got off of Amazon for TLO8. And I forget what the other one is. Not TLO, SOC 8 devices. So this allows you to take these little surface mount devices and let's just get one of these here. There we go. Lets you take these little surface mount devices and mount them in through-hole applications. There's a little plus sign right there. So this is pin 1. All right, so we're going to put this on this away. Now, how are we going to do this without modern microscopic equipment? Well, we're going to do it this way. I don't know if this is the right way. I don't have any solder paste. Actually, I do have solder paste, but I don't want to do it with solder paste. I want to do it with my hands. And what I'm going to do is I'm going to put just let's clean this guy off. All right, and get a little solder. I'm going to put a little bit of, just a little bit of solder on that one. That sucks. How about that? Hopefully I haven't heated it too much. Don't matter because we're going to use what we got. Let's see if I can. Okay. Looks like it's done. Okay, what I'm doing is I'm putting this on a breadboard so that it's easier. So I just put 2 4-pin headers in there, and let's pop. Boy, oh boy, I say. Let's just pop this. It really doesn't matter at this point which way it goes, does it? Okay. There we go. Now we'll put it on the. There are many well-known techniques for desoldering in the rework industry. I don't know what any of them are. What I use is this thing. So this is a Weller desoldering sucker thingy, and I'm going to use a combination of that and this wick to get the solder out of here. So let's see if we can do that under the microscope. So I must confess, I'm going to try to do all the removal and all the removal at once and all the insertion at once. So for everything that I have a part for, I'm going to remove. I've used the solder sucker on this, but you know, it's not like you just suck the solder out and everything goes fine. You've got to get the residuals out there. These are through-hole pins, through-hole, there's metal through the holes, so there's solder in the holes itself, and even if you get the superficial solder out, if the sucker hasn't pulled it out from the inside, you're not going anywhere. At some point, so I just yanked one of these out. At some point in the process, what you realize is that the pins are no longer being held in by solder, but rather by mechanical action. And you can usually tell the pins become free because from the bottom they start jiggling independently. You know, they start moving around even if they're not heated. And that says that they're free of any solder in the plating in the holes themselves. But what you want to do is you want to be really careful because you don't want to be ripping off these pads. Right, and in these through-hole plated versions, you can now solder in the inside, And you can have solder on the top. So if we go to the top here, and we look at this guy, let's focus, yeah. You see we can get solder around the edge here because it flows through from the bottom. And you want to get all of that out. And unfortunately, the soldering iron has to be really hot for this. So whatever part you're doing this to is pretty much destroyed by heat when you're done with this process. So you better have another one. And even though I said I wasn't going to replace this 7404, I am, because I am. All right, so let's see if we can begin to pry this up. A little force. Yep, here it comes. And we'll just use a little heat to help us. This guy seems, there we go. All right. He's out. Just an FYI here. In any professional circuit board design, what you're going to find is the way the ICs are laid out is the little U-shaped thing is always pointed in the same direction. So this little U here, which indicates that this is pin 1, and you also see a square pad here, is the same on this one, which is kind of gummed up because, you know, we're using this SMD component, but same on this one. This is pin 1, the little U should be there, and this component, which we haven't touched, you notice the U is here, and this is pin 1, and the same all along. So if the board is done by pros, you know, and in a commercial product, you almost always see that. Now, it isn't always true. You get some crappily made boards, and, you know, the U can be in all different directions. But when you're starting to do rework like this and you're taking stuff out, always, you know, chances are if you can't remember which one is pin 1, well, pin 1 is usually got a square or some octagon or some way to note. See, this has got that little white spot, plus it's square and the rest are round, plus it's showing you the U. They all tend to be in the same direction. Kind of a rule of thumb, not always true, but we'll see. All right, so there's a new TL084, and we're going to pop that in, and we're going to pop this guy in, and now we're going to solder them all in. All right, now I'm going to go after these triacs here, and they're soldered in a unique way. The two end pins, let's look at this one over here. The two end pins are soldered straight in, and the middle pin comes down and is soldered there. Interesting, they may have had a different part in mind, or maybe that's, I don't know. Maybe there's probably a perfectly good reason for that. But what you can see from the back is there's a boatload of solder on there, on each one. What I might do is just replace the blue and the green, because those are the ones that I'm flipping between the most often, and I don't seem to go through the other ones. So just for the sake of expediency, I think I'm just going to replace those two right now, because that's a whole lot of solder, and I'm going to use a ton of wick trying to get it up, and I don't even think I can use my solder sucker on something that lumpy. All right, so this is the blue one right there. Let's see. Let's see what we get. Yeah, it's pretty lumpy. There's a lot of solder on that thing. No, we barely made a dent. Yeah, that worked. Let's try that one. Huh. Well, maybe it is not as bad as I thought. Okay, I got those out with sheer malice and barbarism. What I wound up doing was cutting them because, you know, they got this big heat sink on the back, and so you try to desolder and the heat sink absorbs the heat like it's supposed to. So I cut them off, and then I just took the little bits out, which was much easier to do. But clearly the guys who put this together did not think that someday some poor son of a woman from New York City was going to have to desolder them. They figured they were built for to last forever. That was their theory. And they weren't intending for these things to come apart as brutally as I have just taken them apart. All right, now, and I'm looking here and I'm seeing what the heck is that? You know, that's some of that that heat paste, which we're going to have to put back on everything. Here's one over here. It might be a little easier to get out, and I'm not even sure I have to take it out, but I'm gonna because I've got some extra. So what I'm gonna do is I'm just gonna cut it off and slice. See, oh, there it goes. There, now it is gone. All right, now we can use the solder sucker on the back here, and it will be, let's see if you can see it. Get the solder sucker in there, yeah. It's removing a lot less, you know, there's a lot less heat mass behind the whole thing here. So it's a little bit, ever so slightly easier to get the solder off. All right, we size this guy up and let's solder him in. What temperature are we on here? How the hell do I get to a lower temperature, by the way? All right, now we're on a lower temperature. All right, good. I don't want to be burning these things up as I'm putting them in. All right, that looks a little better. And clip off the leads. And you see that guy's on there. So we basically have to take this and create this scenario. This is a little wonky. There we go. And now let's try to fit it on the board. And it is, you know, when they make these things in the factory, they have a jig. They just put this bad thing on a jig, and everything is sized correctly because they're making hundreds of them. I'm doing this once in a lifetime. Thank God I don't have to do this for a living, or I'd be pretty unhappy. This is just a little hobby thing we're doing here. All right, will that go in now? How about now? Oh, I see. This hole right here is not completely free of solder. I'm going to have to clear it out with the sucker. That looks better. And man, with the contrast, it's really good to be able to see if you could see through there, but you'd have to put a light on the bottom. All right, let's try that now. Let's see if we can convince it to go in there. Try this. Still looks like there's a little bit of solder in there, doesn't it? Yeah, there's more than a little bit of solder in there. All right. We'll get a little wick here and see if we can coerce it out. There we go. I see we're going to have the same problem over here on this one. And let us convince it to come out. There we go. Those look like nice holes now, which we are about to fill up with solder again. All right, let's put this guy in. Now he fits. Is he the same height as the other ones? We need him to be the same height because there's a bunch of screws that go in on the other side. That's probably good. Right there. So here's all the parts we took out. You know, there's probably a more sensible way to do this than the wanton replacement of parts just because you can. You know, all of these semis might be fine. Chances are the actual problem was in one of these passives. That one of these high-end resistors went out of spec. I mean, I could replace every one of those. You know, it could be one of these caps, although they're all testing fine. You know, I just can't say. I also replaced these These FETs, which are the ones that lock, I mean, there's no reason for it. They just lock up when you're in an overvoltage situation. But who knows what kind of weird feedback you get. You know, just for the hell of it, I'll clean up these connections over here.
Okay, now we're going to go for the smoke test. Board's back in. Quite a bit of heat sink material I put in. And I'll let you look at the front lights. Here we go. On 3. 1, 2, 3. Alright. It says we've got regulation. I don't see any smoke coming out. So the parts we put in are probably working. Let's get the meter and do a little testing around. Okay, now what we'll do is let's just test, I'm just going to test the output voltage. Output voltage is 122. And now I'm going to test the two triacs I put in. One is right there, 123, and one is right here on the green, 116. Okay, and I don't sense any hunting, but then again there's no load on it. So what we're going to do is I'm going to try to case it up. I'm going to put it back in the rack, and I'm going to put a load on it, and we'll see if it starts hunting. It's not hunting now, but then again, it never did hunt when it didn't have a load on it. The main thing is the parts we put in seem to be working. There doesn't seem to be any issue with that. Okay. Okay, this output is actually on the, this audio output is actually on the Furman here. I'm going to get this wire the other way. You can see we're in regulation. We're not showing any signs of hunting. It's been on for about a half hour now, no hunting. I'm going to leave it on for a while and we'll see if it goes back, but for now it looks rock solid. I'm going to declare this a win, and if not, hey, we'll come back and replace a few more parts. I did wind up cleaning off all the flux. I went outside, got some flux cleaner and a brush. I don't have an ultrasonic cleaner. And I did clean off the flux. I did resolder some of the more flaky looking connections. For all I know, the hunting problem was due to a flaky connection and not due to anything I replaced. But the good news is at least the stuff I replaced seems to be working just fine. Okay, so that's that. Hey, thanks for watching. I'm Joe. If this was of any use to you, I'd appreciate a thumbs up or a comment, or just let me know you're out there. And if you like the sort of stuff we're doing on the channel, which is to mess around with electronics, we're going to get into some musical things in a couple of videos. We'll do some synthesizer work. We'll do some playing piano. And then we'll get back into the Tesla coils and making the Tesla coils musical. And if you like any of that, please subscribe. It helps me out if you do. And thank you very, very much for your time. Really appreciate it.